Today we're going to look at ideal gas law, which is another way of calculating moles. We can use ideal gas law when we're not given specific ranges like STP or SATP, but something that is a little bit more out of the norm. So we're going to do two things with this lesson. First, we're just going to go through a simple PV equals nRT question, and then we're going to use a stoichiometry question. So PV equals nRT, where P is pressure and it's in kilopascals, V is in liters, V is volume in liters, N is moles, R is universal gas constant, and its number is 8.31, and T is in temperature. Now this temperature is in Kelvin. To get Kelvin, you're going to take your Celsius and add 273 to it. So here is Port Coquitlam, British Columbia, where I'm sitting in right now, and oops. Scroll up here one second. Here's Port Coquitlam, British Columbia, and what we have is a couple values. I have a temperature at 14 degrees Celsius. I have a pressure at 102.56 kilopascals. And so we're going to use this data to calculate our values. So what's the volume of 3.0 moles of oxygen gas right now in Port Coquitlam? So the pressure is 102.56. My volume's on my unknown. My number of moles is 3.60. My R is always 8.31. And my temperature is 14 degrees. I add that to this 273, so I get 287 Kelvin. So PV equals nRT. I want to solve just for volume, so I'm going to divide both the sides by P. So V equals nRT divided by P. I simply then just plug in my values to get what I need. So volume equals 3.60 times 8.31 times 287, all divided by 102.56. So that gives me 83.7 liters of oxygen gas. So how do we use this in stoichiometry? So a question would be like, how many liters of chlorine gas at 100.3 kilopascals and 35 degrees Celsius would the decomposition of 2.50 moles of sodium chloride produce? So first off the bat, what we're going to do is we're going to balance our equation. So that's our step one right here. Balance our equation. Number two, find our given and unknown. Our third step would be to calculate the mole ratio. So far we have our decomposition and our balance. Our given, as stated in the question, is 0.250. These other pieces right here are used for these guys here, this 100.3. and the 35 degrees, that's going to be used towards the end of the problem. So what we have now is we have a mole ratio of NaCl over Cl2 equals 2 over 1. And then we're going to take that and plug in our values. So our values in this case are 0.250 moles from the NaCl over X equals 2 over 1. So when we do that, mathematically we get 0.125 moles of Cl2. Once again, we're solving for volume. So PV equals nRT becomes V equals nRT divided by P. Our volume is 0.125 times the universal gas constant, 8.31, multiplied by 273 plus 35, and divided by 100.3 kilopascals. So we get 8.39 liters of Cl2 will be produced. I hope this helps you understand how we're going to use universal gas law and stoichiometry.